Hello everyone, welcome to the GATE Academy GATE Score Booster sessions. In this session, we are going to discuss about signals and systems part 2. We have already discussed about part 1. So I think the session is live, correct?
Yes, sir.
Hello everyone, please respond. How is it going? Have you all attended yesterday's session? The first part of signals and systems. Hi Priya, hi Shiva, hi Supriya, hi Sandeep. All of you who are the part of the session, please respond. So what did we cover in the last session? We have completed our first chapter, right? We have completed our first chapter and almost in the verge of completing the second chapter. Okay. First chapter being very important, correct? The first chapter is very, very important in the point of view of understanding. And also there are quite a few important topics in the first chapter. Whereas second chapter is very simple. As we have discussed, it revolves around the concept of convolution, right? It revolves around the concept of convolution, and the questions will be based on continuous time convolution or discrete time convolution. More often than not, questions will come from the properties. And in fact, we have seen the quiz for LTI systems, and also we have gone through one problem and one more problem we thought of discussing today, right? And once we complete LTI systems, we will move to the third chapter, which is one of the most important chapters of signals and systems, that is continuous time Fourier analysis. So as a part of continuous time Fourier analysis, we will be discussing Fourier series and Fourier transform. So before going into that session, before going to the next chapter, so let us complete the problem solving of this particular question, which you can see on your screen. Hi Sandeep, yes, the GATE schedule has been announced. Yes, I think now you have a clarity about your dates, right? We have a clarity about our dates. Now this is the time to become more focused, isn't it? Because now the dates are announced. Now we have a better visibility of the examination. Hi Kaustubh. Yes, if any of you have missed the last session, then please make sure that you are providing sufficient time to watch that session. It's a very important session. I'm sure the students who have attended the last session have realized how important the GATE score booster sessions of signals and systems are. Right. So what is our major target? Our major target as a part of the signal booster session is to complete or cover all the important areas, of signals and systems, and also realize where we generally make mistakes. It's very important to understand. So when we are solving these problems, the problems are framed in such a way that they will encourage you to make mistakes. And when we solve this problem, when we discuss this problem, then we realize the kind of mistakes that we can do. And once we note down all these mistakes, then it will be better for you in terms of preparation for your examination, because whatever mistakes students commit, all those things I have accumulated in this session, and while providing the solutions, I will be telling you what are the common mistakes that are done by the student as a part of solving this problem. So Kaustubh is very regular to my sessions. Quite a few times of the webinars I've taken, he is actually part of it. That's okay, Kaustubh. I think you could not wake up early in the morning yesterday. or you might not have been aware of the session of signals and systems. That's okay. It's available recorded. You can watch it. I think few more participants have joined. Sumit has joined. Yes. Rajashekar, Srinivas. A very good afternoon. Yes. So Vaishnavi is asking for homework problem answers. Okay. I will provide you a link. Okay. I think it will be part of your description. It will be part of the description. You can see the link. In the link, you will be having the yesterday's session, whatever notes we made in the class. Along with that, I have also provided solutions for the homework problems. Okay. So if the link is not visible in the description, please let me know. At the end of the session, I will be providing you the link. That's very good, Shiv Prasad. So Shiv Prasad says that so he's shortlisted for ISRO examinations, how to prepare for interview, even though that's not an agenda of this session that we are doing today. But please remind me, I will tell you at the end of the session. Shanwaz Pitan Pramanik. Very good afternoon. Kaustav, yes, Fourier series is very important. Fourier analysis itself is a very important part of signals. You're right. So the students who haven't watched the last session, please make your time to watch the part 1. This is part 2 of signals and systems. Okay, please make your time. We'll complete the part 2. And then after completing this session, if you have time today, you can watch today. Otherwise, you can watch tomorrow. Sumit, can I know your stream? Hi, Rick. Good afternoon. Yeah. So let us solve this problem. Let us solve this problem. First of all, let us understand the problem. It's very important, my dear students, to understand the question carefully. Sumit, I think you are from electronics and communications. If you are from electronics and communications, digital filters has been removed from the syllabus. Digital filters has been removed from the syllabus. FFT and digital filters both are removed from your syllabus. Okay. So consider the cascaded system with impulse responses H1 of n and H2 of n. So we are having the impulse responses H1 of n and H2 of n. Now they are connected in cascade, right? They are connected in cascade. Input is x of n and output is y of n. Input of the system is x of n and output of the system is y of n. H1 of n is given in the question, which is 1, 2, 3. The arrow is important. So arrow is present at 1. Arrow indicates n is equal to 0 sample, isn't it? Similarly, H2 of n is also given to us, which is 1, 0, 1. Now, what we have to do is to find out the output of the system. We have to find out the output of the system at n equal to 3. You have to find out the output of the system at n equal to 3. What is interesting here is what is x of n, isn't it? So the representation of x of n is a little complicated, isn't it? X of n is given as maximum of mod of del of k, where k changes from minus infinity to the value of n. The k changes from minus infinity to the value of n. Now the interpretation of this is very important because the similar thing has been asked in GATE 2020. So I try to a little bit mimic the GATE paper of 2020. So in 2020, what has been asked is that y of n is equal to integral, summation, not summation, maximum part of k from minus infinity to n, okay, mod of x of k. Okay, this was provided and the question was to find the impulse response. The question was to find the impulse response. The important thing here is that how to interpret this. Now, how do we find the impulse response? How do we find the impulse response? This has been asked in GATE 2020 paper. This has been asked in GATE 2020 paper to find out what is the impulse response. My dear students, it's very simple. First of all, what is impulse response? Impulse response is the response of the system or the output of the system when the input is impulse, right? When the input is impulse, then the output of the system is nothing but the impulse response. Yes or no? The output of the system is nothing but the impulse response. When the input is impulse, the output of the system is nothing but the impulse response. Now, this is similar to what has been given here, isn't it? Maximum of k from minus infinity to n mod of del of k. And I've seen that quite a few students have marked it wrong. Okay. So let us discuss this. First of all, the systems are cascaded, right? H1 of n and H2 of n are cascaded. Now, whenever two systems are cascaded, can you please tell me how to approach the overall impulse response? The overall impulse response is given by the overall impulse response. So we are finding out the overall impulse response of the cascaded system. We are finding out the overall impulse response of the cascaded system. That is given by H1 of n convolved with H2 of n, right? So this comes from the cascading property of convolution. This comes from the cascading property of the convolution. By mistake, many students, when they try to see the cascaded systems, they will write the overall impulse response as, instead of doing convolution, they'll do multiplication. Instead of doing convolution, they do multiplication. Okay, because something we learn in control systems, where if you are given two systems gain, then the overall gain is given by the multiplication of the gain. But we have to understand that is there in Laplace transform. I'm sorry. The gain is there in the Laplace transform. So when you write two systems, G1 of S and G2 of S, the overall is going to be given by G1 of S multiplied by G2 of S. But that is there in the Laplace transform. But when you convert into time domain, the multiplication becomes convolution. That is the reason why you have something like this. Okay, so this is one of the mistakes that students do. They by mistake write multiplication in the place of convolution. By the way, we know how to do the convolution, right? If you are having two discrete time samples, if you're having two discrete time sequences, then how to find out the overall. So how to find it out? I think I already have the answers from Priya and Sahan. In fact, overall answers are also been provided by Amartya. I think Shiva Prasad is also given the answer, but I think he modified the answer now. Okay, answer is 9. Let us see whether that is correct or not. But I really appreciate within short notice you are able to answer the problem. That's very good. So let us see the tabular method, right? So you have given two sequences, 1, 2, 3 and 1, 0, 1, isn't it? So 1, 2, 3, 0, 0, 0 and again 1, 2, 3. So if you draw the diagonal and then add the diagonal elements, then the resultant is going to be 1, 2, 4, 2, 3, isn't it? Now, where is the arrow position? The arrow position is going to be here. Okay, so lower limit in both the cases is 0. The lower limit in both the cases is 0. The resultant lower limit is also given by summation of the lower limits. Summation of the lower limit. The resultant lower limit is given by summation of the lower limits. So you're going to have 1, 2, 4, 2, 3. So this is nothing but the overall impulse response. This is nothing but the overall impulse response. Now you have overall impulse response. You have to find out what is this x of n, right? Now let us take different values of k and then arrive at the conclusion. We know that whenever you are having an impulse, so impulse, let us say del of n you are having, it is going to be given by what? 1 at n equal to 0 and all the remaining samples are zeros, right? All the remaining samples are zeros. So this is what we know about del of n. This is what we know about del of n. Now what we have to find is what is x of n. What we have to find is what is x of n. So what we will do, we'll take different values of k. So let us take the value of k is equal to -2. So if I take the value of k is equal to -2, so what I have to do here, x of n is nothing but maximum of mod of del of k, where k is changing from -infinity to n. So here I am finding out the value of not k, n, right? At n equal to -2, we are trying to find out x of -2. So if you're finding out x of -2, what is this going to be equal to? K changes from -infinity to -2 and mod of del of k. So we have to find the maximum value of mod of del of k in this range. We know all the samples are going to be 0 for impulse except k equal to 0. So you are taking the region of -infinity to -2. So it means that in all this region, del of k value is going to be 0. So maximum value of 0 is going to be 0 only. Similarly, if you take x of -1, so you're taking it from -infinity to -1, still all the samples are zeros, isn't it? From -infinity to -1, you're taking the maximum value of del of k. In fact, you're having all the values are zeros. So maximum value of then is going to be equal to 0 again. Now, when you talk about x of 0, now you are taking the value of x from -infinity to the value of 0. -infinity to the value of 0. Now, when you take it from -infinity to the value of 0, can you please tell me? Then you are going to have the maximum value of del of k is going to be what? You're taking all the samples from -infinity to 0. So all the samples will be 0 except k equal to 0. At k equal to 0, we are having what? At k equal to 0, what do we have, my dear students? At k is equal to 0, what do we have? We are having 1, right? We are having 1. So it means that you are taking the maximum value of 0, 0, 0, 1. Then the maximum value is going to be equal to the top. The maximum value will be equal to what? The maximum value simply will be equal to 1, isn't it? Because from -infinity to 0, all the other samples are 0 except k equal to 0. At k equal to 0, we are having the value equal to, at k is equal to 0, we are having the value equal to 1. So thereby, you are going to have the maximum value here is going to be equal to the top 1. The maximum value here is going to be equal to the top 1. Is that clear, all of you? Okay. So what about x of 1, my dear students? What is x of 1? Now you are taking it from -infinity to -1, isn't it? You're taking it from -infinity to -1. So from -infinity to -1, I'm sorry. You're taking it from -infinity to 1, isn't it? So from -infinity to -1, it is 0. All the samples are 0. At 0, the value is 1. At 0, the value is 1. At 1, because we are taking it till k equal to 1. We are taking it till k equal to 1. What is the value at k equal to 1? The value at k equal to 1 is going to be equal to 0, isn't it? The value at k equal to 1 is 0. The value at k equal to 1 is 0. So what is the maximum value? What is the maximum value? What is the maximum value? Again, it is going to be equal to 1. And similarly, x of 2, again -infinity to -1, all zeros. At 0, there is 1. At 1, there is 0. At 2, also there is 0. At 2, also there is 0. Again, x of 2 is 1. It means that you are getting the x of n. You are getting the x of n as 0, 0, 0, and so on. At arrow position, you are having 1. At arrow position, you are having 1. And after that also you are having ones. It means that this is u of n, isn't it? I think Priya has answered it correctly. Very good. Amartya has also answered it correctly. That's absolutely correct. So x of n here is going to be equal to u of n. X of n is going to be equal to the top u of n. That's absolutely correct. Now let us see what is the answer, because now we know what is u of n and what is h of n. So h of n, u of n convolved with h of n is equal to h of n convolved with u of n. And we know whenever you are convolving anything with the top of the step function, when we convolve anything with the top of the step function, you are going to have the summation of that function. You're going to have the summation of that function from minus infinity to the value of n. From minus infinity to the value of n, isn't it? So this is going to lead to the summation. Now we have to find the output. This is output, isn't it? We have to find the output where? We have to find the output at n equal to 3. We have to find the output at n equal to 3. We have to find the output at n equal to 3. So from k from minus infinity to 3, k from minus infinity to 3, h of k. And we know the h of k values. We know h of k value, right? This is h of n. Okay. So from minus infinity to minus 1, everything is 0. From minus infinity to minus 1, everything is 0. So we are starting from k is equal to 0 to the value of k is equal to 3. We're starting from k is equal to 0 to the value of k is equal to 3, where your h of k value is non-zero, isn't it? So you're having h of 0 plus h of 1 plus h of 2 plus h of 3. H of 0 is given. H of 0 we just found out. H of 0 is 1. H of 1 is 2. H of 2 is 4. And h of 3 is 2. So h of 0 is 1. H of 1 is 2. H of 2 is 4. And h of 3 is 2. So totally, what is the value we are going to have? What is the value we are going to have? 1 plus 2 plus 4 plus 2, which is equal to 9, isn't it? So the output y of 3 is equal to 9. So many of you have got the right answers, right? Many of you have got the right answers. So h of 3 is a sample, okay? H of 3 is not a signal. H of 3 is a sample value. The value is going to be equal to 9. The value is going to be equal to 9. Okay, so I think Amartya has got the correct answer. Shiva has got the correct answer. Kaustubh has got the correct answer. Sahan, so you will not have u of n because this is actually the sample value. Okay, this is actually the sample value. Is that clear? Can we move ahead, my dear students? Can we move ahead? Can we go to the next one? So the key part of the question is that, of course, you should know the cascading property. You should know the cascading property, but the key important thing is that whether you know this or not, whether you can understand what is given here as x of n or not. Once this is clear, then everything is a simple cakewalk, isn't it? Now, this is homework for you. So please take the snap of this. Please take the snap of this, everyone. Please take the snap of this. Please let me know once you have taken the snap. Yeah, let's go ahead. Okay. So what is given here? In order to succeed, your desire for success should be greater than your fear of failure. I feel this is one of the very apt quotation for us, considering the position where we are in. Okay, so everyone wants to succeed, isn't it? You, me, everyone. We want to taste success. But do we have that desire which overcomes the fear of failure? So whenever we go for any test series, okay, anything like, for example, solving a question. So we always have a fear in our mind. Okay, many students, even though they get a correct answer, they don't express it. Why? They don't express it. The reason is that they think, what if it is wrong? Yes or no? It means that we are not ready to fail. We are not ready to fail. We think we are born to succeed. Okay, so it is a sin to fail. It is a sin to fail. So that is something which stops you from taking risks. Sometimes there are people who have a very good potential. They have excellent potential, but they don't want to take even 1% risk. Okay. And if you don't take any risk, how can you succeed? Okay. Because once you take a risk, you come out of your comfort zone. Now, once you come out of your comfort zone, then you try to do your best. Okay. So fear of failure is something which stops us from being more successful. Okay. You might have this thing in your mind. Okay. When you're going for any examinations, there will be pressure. What will happen if I do a mistake? What will happen if this goes wrong? These sort of fears will always chase us like shadows, right? But remember one thing, my dear students, let us be completely free in our mind. It's very important to be very free in our mind. We should not think too much about what is going to happen, I mean, after 50 days or so. What we have to instead do is to focus on the process. Okay. Our process is that on daily basis, on everyday basis, we have to extract maximum amount of time. We have to wake up early if it is possible. We have to extract maximum amount of time and put the time in our preparation and ensure that proper amount of time is going for revision and writing tests. Okay, so this is what we do at this point of time. Okay, even if you haven't prepared very well till now, but if you are able to utilize your last 50 days of time, then you can do very well. There is a chance that you can do very well, because it's important that you should not be under very much high pressure. You should not be under very much high pressure. Be free. Only thing that we can do at this point of time is try to do our best. Nothing more than that, nothing less than that. Okay. Don't have any fear of failure. What will happen if I fail? What will my what can I answer to my parents if I don't get very good marks? Will my friends laugh upon me? Because unlike them, I have taken a lot of time for preparation. I have sacrificed, I have paid the fees. You know, in spite of that, if I don't get a rank, maybe students will laugh upon me. These things, every time they will revolve around us. But this is the right time to come out of all these things, because one thing that guarantees success is consistent preparation. Okay. So if you are able to utilize your whatever time is there with us, if you are able to utilize it in the best possible manner, then definitely you will be successful. At least you will understand what is the success formula. What is it actually takes to become successful. So my dear students, this is very, very important time for you. This is the time you come out of all the fears upon your mind and try to ensure that you are putting best possible time into your preparation. Don't have any fear, don't have any tension. Don't think that, sir, I have to get top 100 rank only, then only I'll be happy. Don't think like that. Okay, should not worry about the ranks as of now, because sometimes if you are having a pressure of getting a very high rank, if you are having a pressure of getting a very high rank, so every unanswered question, if you are not able to answer any particular question, then you think, ab kya hoga? Okay, what will happen now? Because I haven't answered this question very well. So these things will always go in your mind, will travel in your mind. So it's very important, my dear students, come out of all these fears, because you know, India has won the matches even with a score of 150 runs. Okay, that has also happened, that quite a few times India hasn't batted well, but it has won the match. Similarly, if we haven't solved one problem well, two problem well, three problem well, we should not fear that what will happen, what will happen. Let us have one thing in our mind, that whatever happens, I will try to do my best. Whatever is going to happen, I will put my best foot forward. Nothing else is there in our mind. I mean, nothing else is there in our hands. Only thing that we can do is that utilize our time in the best possible manner and ensure that you are putting your best efforts. Okay, that is what we can do. So my dear students, come out of all the fears and ensure that you are putting your best foot forward and ensure that you are utilizing your time in the best possible manner. Okay, so we are now entering into the very important chapter of signals and systems, that is Fourier analysis. So as part of Fourier analysis, we have two very important concepts. What are they? One is Fourier series and the other is Fourier transform. Okay, now many students have a fear regarding Fourier series. Why? Because there are quite a few formulas. Okay, there are quite a few formulas. There are something like complex Fourier series, trigonometric Fourier series, polar Fourier series, अरे इतना बड़ा फॉर्मूला सेट में क्या याद रख पाऊंगा, नहीं रख पाऊंगा. These things can come into our mind, right? These are big formulas. Okay. Again, there are, I mean, you have to find out the coefficients, right? C naught, CK, AK, BK. Again, these are formulas. So whether I can remember them or not. So looking into a lot of mathematical expressions which are present, many of us get demotivated by this chapter. But unlike all the mathematics which is involved in this chapter, my dear students, this chapter is one of the easier chapter. Why? Because if you see the pattern of the examination, the pattern of the examination as far as Fourier series is concerned is very clear. The pattern of the examination as far as Fourier series is concerned is very clear. So what is the pattern, sir? What is the pattern, sir? You have some note points. What are the note points? Okay, you are having trigonometric Fourier series, complex Fourier series. So let us first of all talk about the complex Fourier series. So if you are having a signal f of t which is periodic in nature, you are having a complex Fourier series coefficient called as CK. Now, what is the first note point? That if this signal is real, what is the nature of CK? If the signal is real, then what is the value of CK? What is the nature of CK? CK satisfies even conjugate property. As a part of yesterday's session, my dear students, we have seen how the even conjugate and odd conjugate looks like, right? So at the arrow position, you are going to have a real number. If you have x comma y here, now you are going to have x conjugate comma y conjugate. You're going to have x conjugate comma y conjugate. This is how the even conjugate looks like. So the questions, if you see, my dear students, the questions revolve around this property. The questions revolve around this note point. That is the reason why your short notes is very important, because it should have all the important note points. If the signal is real, my dear students, if the signal is real, then CK satisfies even conjugate property. If the signal is real, then CK satisfies the even conjugate property. Now, if the signal is real and even, what about CK? If the signal is real and even, CK satisfies nature of real and even. Okay, if the signal is real and even, your CK is also going to be real and even. If the signal is real and odd, can you please tell me what happens to CK? If the signal is real and odd, then what happens to the CK, my dear students? The CK is going to be imaginary and odd, isn't it? The CK is going to be imaginary and odd, yes or no? So these are some very important note points. Apart from that, if you are having trigonometric Fourier series, which is nothing but, what is Fourier series? Very simple. Fourier series is nothing but representation of a signal in terms of sinusoids of fundamental frequency and harmonics. So if you are having any periodic function, now you are going to represent this in terms of sinusoids having a DC component, if at all it has a DC component, and then you are going to have cosine components and sine components. Cosine components and the sine component. This is nothing but Fourier series, yeah. If you're talking about complex Fourier series, then you're just representing it in the form of what? You're just representing it in the form of e power j k omega naught t, where k is nothing but the harmonic number. K is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. So basically you're representing the signal in terms of a sinusoidal function, whether it is cos or sine, or it is e power j k omega naught t, which is also a sinusoidal function. We are representing it in the form of sinusoids of fundamental frequency and its harmonics. That's it. That is nothing but the Fourier series. Okay. Now, when we talk about the trigonometric Fourier series, there are two very important points, that when the signal is real and even, then what is the nature of the Fourier series? The Fourier series will only be having cosine components. The Fourier series will only be having cosine components, right? Yes or no? Out of sine and cosine, sine will not be present if the signal is even. So you will just have the cosine components, and you can also have the DC component. If the signal is real and odd, then you are just going to have the sine components. In fact, this also has been asked quite a few number of times in the examination. This also has been asked quite a few number of times in the examination. So this is very important. So what did we see? The nature of CK, when it is when the signal is real, when the signal is real and even, when the signal is real and odd. The trigonometric Fourier series, when the signal is real and even and the signal is real and odd. So the questions revolve around this concept. Apart from that, you have some properties. You have time shifting property, you have time scaling property, you have time differentiation property. These properties are also important. You have something called as very, very important, extremely important in the examination point of view. What is that? There is a concept called as half wave symmetry. The concept called as half wave symmetry. Now, what is this half wave symmetry? Why are we using this concept of half wave symmetry? This is very important. Even in fact, your 60 to 70% of your problems concept is going to revolve around the half wave symmetry. The concept is going to revolve around the half wave symmetry. See, when you're talking about representing a signal in terms of sinusoids, so the sinusoid is going to have its fundamental frequency, it's going to have its second harmonic, it's going to have its third harmonic, it's going to have its fourth harmonic, it's going to have its fifth harmonic, and so on. Okay, so there are so many number of harmonics. Now, half wave symmetry is a concept which will tell you whether you are going to have even harmonics or not. Whether you are going to have even harmonics or not. If the half wave symmetry is satisfied, then the signal will not have even harmonics. It is just going to have odd harmonics. Okay, if it satisfies the half wave symmetry, the signal will not have the even harmonics. It will just have the odd harmonics. So this concept is very, very important. This concept itself is very, very important. Many of your GATE questions is going to revolve around this concept. Okay, so this is your Fourier series, my dear student. There is nothing else in Fourier series. You just have these node points, you just have these properties, and you have this concept of half wave symmetry. That's it. There is nothing more in Fourier series. It's just you have to solve the problems to get more and more comfortable. You have to just solve more problems to get more and more comfortable. Nothing more than that. Okay. Now, when you go into the Fourier transform is more simpler. Okay. Again, this is similar to mathematics. Okay. You are having Fourier transform formula. Okay, you will have some existence condition of Fourier transform, which is important in the examination point of view. You should know the existence condition. And after that, you are finding Fourier transform for different standard functions. So what are the different standard functions? What are the different standard functions that we have discussed in the class? So we have something like e power minus a t u t. We have something like e power a t u t u minus t. E power minus a mod of t. So all for a greater than 0. And then you are having signum function, signum of t. Okay, then you have u of t, you have the DC component, and then you have the rectangular pulse, and then you have the triangular pulse. Okay, so these are some standard functions. These are some standard functions. So for all these standard functions, you should know the Fourier transform. For all these standard functions, you should know the Fourier transform. I told many number of times, it is not required that you're going to mug up the concepts. It's not required that you're going to mug up the concepts. Okay, it is just you should understand how we are getting the Fourier transform. How we are getting the Fourier transform. We have seen the derivations of how to get these Fourier transform pairs. But with the help of your practice, my dear students, with the help of your practice, if you are able to directly remember the formula, it's a bonus for us. If you are able to directly remember the formula, it's a bonus for us. But you can easily derive these formulas. You can see your notes. It is easy to derive. And if you are able to just have this concept, because the way e power minus at ut is derived, the same way e power at u minus t is also derived. Okay, similarly, if you are adding these concepts, you're going to have e power minus a mod of t. With the same relation, you'll get signum of t. From signum of t, you'll get u of t. So all these things are interrelated. All these things are interrelated. So having the command on these standard functions is very important to solve the problems on Fourier transform. And again, the properties of Fourier transform are important. The properties of Fourier transform are important. The good thing is that Fourier series and Fourier transform properties are very related. Fourier series and Fourier transform properties are very much related. And lastly, you're going to have a concept called as sampling. Now, what is sampling? It's a very simple concept that how you are going to sample your signal from a continuous time to a discrete time. So you have a concept called as Nyquist sampling rate. You're going to have a concept called as Nyquist sampling rate, which says that it should be 2 times that of maximum frequency of your signal. It's going to be 2 times that of maximum frequency of your signal. And the remaining part of sampling, you just need to have a very good command on Fourier transform and convolution. all the remaining part of the sampling concept, you should have a very good command on the Fourier transform and the convolution concept. That's it. Okay, so these are the things about the Fourier series and Fourier transform. So if you are writing your short notes, it becomes very easy for you, because you can just see what are the areas which are important and what are the areas which are not important. Okay, so let us now move into the quiz part. Please try to answer this question. The Fourier series is applicable for all periodic signals. Is this correct? The Fourier series is applicable for all periodic signals. Is this correct? My dear students, please answer this. Fourier series is applicable for all periodic signals. Is this correct statement? Is it correct to say that the Fourier series is applicable for all periodic signals? Yes or no? Yes or no? Is Fourier series applicable for all periodic signals? Is Fourier series applicable for all periodic signals? Very good. The answer is no, because of the presence of this word called as all. Because of the presence of this word called as all. Okay, because Fourier series itself is going to have some limitations, my dear students. It cannot be applied for all periodic signals. That is the reason why we are having something called as the Dirichlet conditions. What does Dirichlet conditions say? The signal has to be absolutely integrable in its period. In its period, the signal has to be absolutely integrable. It should have finite number of maxima minima. It should have finite number of maxima minima, and it should have finite number of discontinuities. It should have finite number of discontinuities. If you are having infinite number of discontinuities, it is violating this. Now, these three are the conditions. If these three conditions are satisfied, we can ensure Fourier series is going to be present for a periodic signal. Fourier series expansion. The Fourier series expansion exists for this particular signal if all these conditions are satisfied. What if any of the condition is not satisfied? Let us say that the signal is not absolutely integrable. Let us say that the signal is not absolutely integrable. Then do we have Fourier series? If all the three are satisfied, then Fourier series expansion is there. But if any of the condition is not satisfied, my dear students, if any of the condition is not satisfied, do we have Fourier series? Do we have Fourier series if any of the condition is not satisfied? If any of the condition is not satisfied, do we have Fourier series? Answer is may or may not. You can still have a Fourier series, or you may not have a Fourier series. Okay, these conditions are what we call as a sufficient conditions. All these three conditions are what we call as a sufficient conditions. Now, what is the meaning of these sufficient conditions? What is the meaning of the sufficient conditions? Sufficient condition simply means that if they are satisfied, Fourier series exists. If they are not satisfied, it may or may not exist. It may or may not exist. So there is a chance that a periodic signal may not have a Fourier series expansion. There is a chance that Fourier series may not have a Fourier series expansion. Okay. So this word all is a dangerous word. This word all is a dangerous word. Fourier series is applicable for periodic signals. It is correct. Fourier series is applicable for all periodic signals. It is not correct. Okay. Okay. So now I think now you will be in a position to answer this question. If a periodic signal is real and odd, then what is the complex Fourier series coefficient going to be? If the periodic signal is real and odd, then what is the Fourier series coefficient going to be? The Fourier series coefficient is real and odd. Is this correct? The Fourier series coefficient is real and odd. Is this correct? If the signal is real and odd, the Fourier series coefficient is also real and odd. The answer is no. The answer is no. It is not going to be real and odd. It is in fact going to be imaginary and odd, isn't it? That is what we have discussed, right? If the signal is real and odd, then the complex Fourier series coefficient is going to be imaginary and odd, my dear student. It's going to be imaginary and odd. Third one. This is a very interesting question. Even though this has been inspired from the GATE question. This has been inspired from the GATE question, but this is very, very interesting question, my dear students. Please try to solve this problem. A complex Fourier series of the complex Fourier series coefficient of a periodic signal is given. So CK is given to us. Now there is a statement here. The periodic signal is complex. It says that the periodic signal is complex with the imaginary part being constant. With the imaginary part being constant, we have to see whether this is correct or not. We have to see whether this is correct or not. Please think and answer. The concept of even conjugate is very crucial here. The concept of even conjugate is very crucial here. My dear students, if you are liking the session, please click the like button, everyone. If you are liking the session, please click the like button. If you have already done it, then ignore it. Ignore this message. Now let us go and see whether this actually satisfies even conjugate or not. Can you answer? Because just now we have seen that the signal x of t, my dear students, the signal x of t, if it is real, then ck satisfies even conjugate, right? Ck satisfies even conjugate. Now, do you think this satisfies even conjugate? Do you think this satisfies even conjugate? Do you think it satisfies even conjugate? Yes or no? It is not satisfying even conjugate. Even though you are having x conjugate here, even though you are having x and x conjugate, this is not real, right? The k is equal to 0 is not real. It means that ck is not satisfying even conjugate property. If ck does not satisfy even conjugate property, then this signal cannot be called as real. This signal is going to be complex. The signal is going to be complex because ck does not satisfy even conjugate property. Ck does not satisfy even conjugate property. Now, do you agree with me that this arrow position k is equal to 0, this component is a DC component? Do you agree with me that this component is a DC component of the signal? This component, what you are having at arrow position, this is a DC component of the signal, DC component or average signal, whatever it is. The answer is yes. C naught is given by what? 1 by t integral its time period f of t dt. So this is the average value of the signal. This is the average value of the periodic signal or the mean value of the periodic signal, which is nothing but the DC component. This is nothing but the DC component. So what I can do now is you have a CK in the frequency domain. You are having a CK in the frequency domain. Time domain, I'm having something called as x of t. Time domain, I'm having something called as x of t. Now CK, what I'm trying to do here is that I am separating the DC component. I am separating the DC component 1 plus j. So I'm removing the DC component and I'm writing it separately. I'm writing it separately, which is possible, right? So if you are having a periodic signal having a DC component A naught, you can just remove A naught and write it separately, right? It is very much possible. Now you see, my dear students, now can you please tell me whether this component is even conjugate or not? Now, when I separate this 2j and write it separately here, now please tell me whether this is satisfying even conjugate. The answer is yes. It is satisfying even conjugate. If this satisfies even conjugate, the corresponding time domain is going to be real. Okay, the corresponding time domain is going to be real. Okay, so x of t, I can write it as the real component and the imaginary component, isn't it? I can write it as a real component and the imaginary component. Now, if this satisfies even conjugate, this is going to be real part of x of t. This is corresponding to the real part of x of t. This is corresponding to the real part of the x of t. Okay, I'm not talking that, I'm not telling, see, please observe my statements here. I am not telling that x of t is real. I am not telling that x of t is real. I am telling x of t is complex. A complex means what? You will be having the real component and you will also have the imaginary component. Yes or no? If you're having a complex signal, you will be having real component and you're having an imaginary component. What you have done here, you have just separated the imaginary component. You have just separated the imaginary component and you have just written the, you have separated the k is equal to 0. You have just separated the k is equal to 0, which is the DC component, and you have written the rest. Now, this is even conjugate. It means that this corresponds to the real component. This corresponds to what? This corresponds to the real component. What does it mean? It just means that the remaining part corresponds to the imaginary component. Yes or no? If this corresponds to the real component, the remaining part corresponds to imaginary component. The remaining part corresponds to imaginary component. Now you see, this is nothing but the DC component. It means that this is nothing but constant. This is nothing but constant. It is like xi of t is equal to 2j. Why? Because this is just the DC component, my dear students. This is just the DC component of signal. The signal imaginary part of x of t does not have any harmonics at all. The imaginary part of x of t, doesn't have any harmonics. It just has 2j and 0, 0, 0. It doesn't have any harmonics. Yes or no? It means that this imaginary component corresponds to the DC component. The imaginary component corresponds to the DC component. Because you have separated the DC component, now this is even conjugate. This corresponds to the real part of the signal, whereas the imaginary part of the signal is the leftover part. The imaginary part of the signal is just the leftover part, which is the DC component. So this statement is absolutely correct, that the signal is complex. My dear student, it says that the signal is complex with the imaginary constant. It says that the imaginary part is being constant. And definitely, yes, that is what we have realized. Yes, the signal is complex. And now we have realized that the imaginary part is constant. What did we do? We again went with the basics. The same note point we have written, that this doesn't satisfy the even conjugate. It means that the signal is complex. Now, we just try to write it separately. This DC component, at any point, I can separate the DC component from the signal. We have separated it. The remaining part satisfies the even conjugate. This corresponds to the real part of the signal. And it means that whatever remaining DC component is there, this is corresponding to the imaginary part of the signal. So this is nothing but the DC component. That is the reason why imaginary part is constant. The imaginary part is constant. Is that clear, all of you? The imaginary part is constant. So this statement is correct. This particular statement is correct. Okay. So please answer this question. If a periodic signal x of t, has a time period of 3 seconds, Ck is a complex Fourier series coefficient, then x of 3t has the complex Fourier series coefficient Ck with the same time period. Is this correct? Okay, so please read the question carefully. You have to do the basics very correct. The basics of the GATE examination is that first thing is that read the question carefully. I know that I am rushing you to answer it quickly, but you should not lose your composure. You have to read at your optimum speed. Understand the question carefully. That's very important. Now, what does it say? You are having a signal called as x of t. It is having a time period of 3 seconds, having a complex Fourier series coefficient as Ck. Then it is asked that x of 3t, does it have the same complex Fourier series coefficient Ck? But more importantly, it says that it is having the same time period. This is the problem, that till here it is correct. That this is what the scaling property of Fourier series says. If x of t has Ck as a Fourier series coefficient, x of 3t is going to have Ck as a Fourier series coefficient as well. But because of the fact that you are scaling by 3 units, Now, can you please tell me what is the period going to be? Is it compression or expansion? Whenever your scaling parameter is 3, you are compressing the signal by 3 units. You are compressing the signal by 3 units. It means now the period is going to be 1 unit. It means now the period is going to be 1 unit. Okay, it's very important, my dear students. X of 3t, A is the scaling parameter, which is 3. So this is the unit of compression, because we have understood this in our classroom that if A is the scaling parameter, whenever A is greater than 1, this is compression. Whenever A is less than 1, this is expansion. This is expansion. So whenever you're having a scaling parameter of 3 units, it means that the signal is getting compressed by 3 units. So previously we had t is equal to 3 as a period. Now you're going to have t is equal to 1 as a period. Till here it is correct. It's going to have the same ck as a complex Fourier series coefficient, but it is going to have different values of time period and frequency. It's going to have a different values of time period and the frequency. Okay. So now the fifth part of the question, while checking the half wave symmetry, should we remove the DC component from the signal? While checking the half wave symmetry, when you are checking the half wave symmetry of the signal, should we remove the DC component? Should we remove the DC component from the signal? Yes or no? Should we remove the DC component from the signal? The answer is yes. Yes is the correct answer, isn't it? Because we have something called as hidden symmetry. We have something called as hidden half wave symmetry. What does it say? That whenever there is any non-zero DC component, then you may not get the correct answer as far as the half wave symmetry is conditioned. What is the condition of the signal? What is the condition of checking the half wave symmetry? What is the condition of checking the half wave symmetry? X plus or minus t by 2, half wave x of t plus or minus t by 2 is equal to minus of x of t. This is what we call as odd half wave symmetry. Generally, when we talk about half wave symmetry, it generally implies odd half wave symmetry only. It generally implies odd half wave symmetry only. So before you go and check this condition, you have to remove the DC component from the signal. That is the first step. You have to remove the DC component from the signal. Otherwise, what will happen is that this condition will fail, and you think that there are no even harmonics. I mean, this condition will fail. What does it mean? If this condition fails, it means that the signal has even harmonics. It means that the signal has even harmonics. Yes or no? If this condition is satisfied, if the half wave symmetry condition is satisfied, then the signal only has odd harmonics. If this condition is satisfied, then the signal only has odd harmonics. If this condition is not satisfied, then the signal will also have even harmonics. The signal will also have the even harmonics. Yes or no? The signal will also have the even harmonics. Correct? So, if you wanted to get the correct answer, the first thing you are going to do is that you're going to remove the DC component. Otherwise, you might have incorrect answer. Okay. Now let us go into our signal booster question. Now we are done with the quiz part. I think now the complete question is visible. Now, as I told in the previous session, I've told you one thing in the previous session, that the questions are framed in such a way to cover more and more number of concepts. Whenever I'm discussing any signal booster question, there will not be one topic, there will be more than one topic. Okay. In GATE examination, there might be only one topic from where the question is going to be asked. So you just try to solve this problem. Don't worry about the time it is going to take, because these questions are going to take more time as compared to the GATE questions, because these are going to be multiple concept questions. These will definitely take more amount of time. The purpose of framing such questions is so that we can cover as many number of topics, as many number of important topics as possible. So never ever get demotivated by seeing the length of the question. By seeing the length of the question, let us try to focus on solving these problems and take the learnings with us to our home. In fact, we are at home only, right? Okay, so whatever mistakes you are committing, not only here in your test series also, please ensure that you are maintaining a record of it. Right, so let us solve this problem, everyone. Let us solve this problem. So here we are having square pulses, right? Square pulses and also some sort of triangular pulses. This is what we call a sawtooth. Okay, so x1 of t, x2 of t, x3 of t, and x4 of t. These are the signals we have. Now the thing is that which of the following is or are correct? Which of the following is or are correct? x1 of t has only cosine term of odd harmonics with DC component. x2 of t has both sine and cosine terms of all harmonics and DC component. x3 of t has only cosine terms of odd harmonics. x3 of t has only cosine terms of odd harmonics. x4 of t has only cosine terms of odd harmonics. See, whenever we are talking about odd harmonics, it means we have to check the half wave symmetry concept. Whenever we are talking about sine and cosine, we have to see the symmetry of the signal, whether the signal is even or odd. Okay, so these concepts are different. Okay, symmetry and odd half wave symmetry both are different. Okay, symmetry means what? Even signal, odd signal. Half wave symmetry means what? Half wave symmetry means what? Okay, so x of t plus or minus t by 2 is equal to minus of x of t if you are talking about odd half wave symmetry. Generally, we talk about the half wave symmetry only, right? So when we talk about even and odd, then we are saying that whether the signal is going to have cosine component or sine. Even, the signal will only have cosine component. If it is odd, the signal will only have sine components. Whereas half wave symmetry will talk about the harmonics of the signal, right? Half wave symmetry will talk about the harmonics of the signal. Now let us see the first option. x1 of t has cosine terms of odd harmonics with the DC component. With the DC component, the answer is yes. The answer is yes. See, whenever you're having a rectangular pulse having 50% duty cycle, whenever you're having a rectangular pulse with 50% duty cycle, what is a 50% duty cycle? 50% duty cycle means on, off, on, off, on, and off. So whenever you are having a signal with 50% duty cycle, where on and off both are having same duration, on and off both are having same duration, this will by default satisfy odd half wave symmetry. This will by default satisfy odd half wave symmetry. But as I told, before doing this, we have to remove the DC component from the signal. What is the DC component of the signal? Can anyone tell me what is the DC component of the signal? Minus 2 to 2 is the period. Minus 2 to 2 is the period. So in this period, you are having an area. You are having an area of how many units? 4 units. So period area of minus 2 to 2, minus 2 to 2 f of t, the area divided by 1 by t. Okay, so the value is going to be equal to 1 unit. Okay, the value is going to be 1 unit. Is it 1 unit or 2 units? Is it 1 unit or 2 units? I think the area is 8, right? The area is not 4, the area is 8. 4 into 2 is 8, right? So 1 by t, where t is the period is 4 units, right? The period is 4 units. The area is 8 units. The area is 8 units. So 2 is the DC component which is present in the signal. If you remove the DC component, what will happen? If you remove the DC component, then the signal becomes something like this. Now you can check the half-wave symmetry, this will satisfy. Now you can check the half-wave symmetry, this will satisfy. The signal is even, no doubt about it. It means that it will have only cosine components. Signal is even, no doubt about it, it will have the cosine components. And the second one is that it is having odd harmonics. Yes, because the signal is having 50% duty cycle. It is having 50% duty cycle. It will satisfy odd half-wave symmetry. It means that it will have only odd harmonics with the DC component. It will have only odd harmonics with the DC component. The first statement is correct. Let us look into the second statement. The second statement says that x2 of t has both sine term and the cosine term. It says that it is having both sine term and the cosine term. Let us try to remove the DC component from the signal. Let us try to remove the DC component from the signal, everyone. Please try to remove DC component from the signal, everyone. What is the DC component? What is the period, first of all? 1 by t integral 0 to t f of t is what we can do here. So time period is 2 units. The time period is 2 units. What is the area? What is the area of this triangle? Half into base into height. This integration is nothing but half into base into height. Base is 2 units. Height is 2 units. It means that the DC component is 1 unit. It means that the DC component is 1 unit. Now, if you remove the DC component, if you remove this DC component, now the signal will be something like this. If you remove the DC component, now the signal will be something like this. Yes or no? This is how the signal is going to look like if you are removing the DC component from the signal. Yes or no? If you are removing the DC component from the signal, this is how it is going to look like. Yes or no? This is how the signal is going to look like. Now, you see whether this signal is odd or even. You have removed the DC component. Now you see whether the signal is odd or even. The signal is odd. The signal is odd. How, sir? Because the best way of recognizing the odd signal is that whatever information you are having in the right side, the same thing with the opposite is going to be present at the left side. So here you are having a line. Here you are having a line which is present in the fourth quadrant. Now here you are having the same line with a minus of this. This is there in the second quadrant. Okay, so whatever information you are having on the right side, the same information with the negation is present on the left side. The same information with the negation is present on the left side. This is an indication that it is odd. But this is what we call as hidden odd, right? Because this odd nature is hidden inside the DC component of the signal. Once you remove the DC component, now you can see that it is odd signal. Once you remove the DC component, this is satisfying what? This is satisfying the odd nature of the signal. So it is satisfying odd nature of the signal. It means that it will not have cosine components. It will not have cosine components. Why, sir? Because this signal is satisfying the odd symmetry. This is satisfying the odd symmetry, which is of course hidden inside the DC component. So once you are able to remove the DC component, now you see whether it is going to be odd or not. So it is odd. So it will not have cosine terms. So this option is eliminated. This option is eliminated. What is the third option? The third option says that it is having only cosine terms of odd harmonics. The problem here is that even though the signal is clearly even, whatever information you are on the right side, whatever information side, the same information is present on the, which is an indication that this signal is even signal. Yes or no? That this signal is even signal. It is an indication. Whatever information is present on the right side, the same information is present on the left side. So whenever this is there, it is an even signal. So if it is an even signal, it will only have cosine terms, no doubt about it. But the problem is that this signal doesn't have a I hope I'm audible. Am I audible, everyone? Please answer. Are you all following me? So x3 of t is what we were discussing here. X3 of t is what we were discussing here. So x3 of t, even though it is even, but because the duty cycle is not 50%, and you will see from this half-wave symmetry concept also, after removing the DC component, if you check the half-wave symmetry concept, this will not satisfy. Okay. So in the examination point of view, we can remember that whenever the signal is a rectangular pulses, periodic in nature, whenever it's having a duty cycle of 50%, it's going to be satisfying odd half-wave symmetry. Otherwise, it will not satisfy. Otherwise, it will not satisfy. So here, because it will not satisfy the odd half-wave symmetry, the signal is not going to have only odd harmonics. The signal will also have the even harmonics. The signal will also have the even harmonics. And the last one says that the signal has only cosine components of odd harmonics. This will also be satisfied. What you have to do is that you have to remove the DC component. You have to remove the DC component and check whether the half-wave symmetry will be satisfied or not. The answer is the half-wave symmetry will be satisfied, and without any doubt the signal is going to be an even function. Without any doubt the signal is going to be an even function. When the signal is even function, this will definitely satisfy, that it will only have cosine components and it will satisfy half-wave symmetry. So thereby it will have only odd harmonics. It will only have odd harmonics. It is also having a DC component. You can see that from -1 to 1 you are having a triangle. So now you can find out the average value. This will come to 1 unit, right? This will come to 1 unit. It means that it is having a non-zero DC component. It is having non-zero DC component. So the first option is correct and the last option is correct. So the answer for this question is A, D. The answer for this question is A, D. Okay. So can you explain the third point? This is a question from Kaustubh. So Kaustubh is asking the question to repeat the third one. So Kaustubh, what I told is that whatever information is present on the right side is same as it of whatever information is present in the left side, it means directly we can say the signal is even. This is the first point. So when the signal is even, it will only have cosine terms. The second point I told you is that this signal is not having a duty cycle of 50%. This signal is not having a duty cycle of 50%. If the signal doesn't have a duty cycle of 50%, then it will not satisfy the half-wave symmetry concept. Then it will not satisfy the half-wave symmetry concept. So what I would suggest you is that after completing this session, okay, what you can do, you can remove the DC component and check the half-wave symmetry formula. You will see that this will not be satisfied. You will see that this will not be satisfied. So the signal will be having cosine terms. This is correct, but it will be having odd and even harmonics. It will be having odd and even harmonics. Okay. So now let us go for the next question. Let us go for the next question. 1 second. Acha. That's okay. Okay. So this is the question from Fourier transform. This is the question from Fourier transform. Please take this question, everyone. Good, Kaustubh. I hope last question has given you very good learnings, because half wave symmetry is very important. Half wave symmetry concept itself is very important. And now by covering this problem, we will be also looking into the Fourier transform part. So anyone got the answer? Anyone got the answer? So the first one, the first part of the question is that, so you're having area integration minus infinite infinity sine 4t by pi t whole square dt is equal to 8. So Shiv Prasad is answering it as B comma D. Okay. B comma D. There was a question from Kaustubh that does the MSQ question has a negative marking? The answer is no. The MSQ question does not have any type of negative marking. Okay. So one thing we should realize is that whenever you're having sine omega ct by pi t, this is going to give you the Fourier transform as, this will give you the Fourier transform as what? The Fourier transform of this will be minus omega c by 2 omega c by 2. Okay, so it will be a rectangular pulse. It will be a rectangular pulse. So whenever you are having sine omega ct divided by pi t, this will be having the Fourier transform of something like this. Now, my dear students, Now what we are doing here, we are squaring the signal and integrating it. It means that we are finding the energy, isn't it? Whenever you are squaring and integrating it, we are actually finding the energy, right? Now, in the place of omega c, you are having 4. In the place of omega c, you are having 4, isn't it? So it is sine 4t divided by pi t. Sine 4t divided by pi t. This will be what? This will be minus 2 to 2, minus 2 to 2 and 1 unit. Yes or no? Now, this is the Fourier transform idea, students. Okay, if this is x of t, this is x of omega. The point here is that we are finding out what? We are finding out what? We are finding out the Fourier transform, isn't it? I mean, we are finding out the energy of the signal. So, energy is equal to integral minus infinity to infinity f square of t dt. This can also be found out with the help of frequency domain 1 by 2 pi integral minus infinity to infinity mod of x of omega whole square. Mod of x of omega whole square. Yes or no? Which means that 1 by 2 pi, what is the area of this function? This is x of omega, mod of x of omega whole square. What is this? What is this? It's going to be 4 times 1, because square of 1 is going to be 1 only. Square of 1 is going to be 1 only. So the area of this is going to be 1 square, which is 1 multiplied by 4. So this is going to be something like 2 by pi. This is going to be something like 2 by pi, isn't it? Yes or no? This is going to be something like 2 by pi. So it's not matching with the answer. It's not matching with the answer. So option A is not correct. Option A is not correct. Let us now see the option B. See whether option B is correct or not. See whether option B is correct or not. So we are finding, I mean, whenever you are having something like sine t by t, something like this, we will never find the energy directly like this. We will take its Fourier transform and then find out the energy of it. We will take the Fourier transform of it and then find the energy of it. Okay. Next question. Next question. Yes, I'm sorry. Yes, it is from minus omega c to omega c. Correct. It's from minus omega c to omega c. That's correct. So by that logic, it's going to be from minus 4 to 4, isn't it? This is from minus 4 to 4. It's a small typo from my side. Forgive me. Okay. So in that case, this is going to be what? This is going to be 8. So this is 4 by pi. This is 4 by pi. Okay. So if you forget 1 by 2 pi, then you are having 8. If you forget this 1 by 2 pi, then you are going to have this 8, right? So you should be a little careful. Next part of the question, integral minus infinity to infinity e power minus 4t ut cos 2t. Whether we are having 0.2 or not. Whether we are having 0.2 or not. Everyone. First thing is that e power minus 2t ut, I'm sorry, e power minus 4t ut, right? 4t ut, what is the Fourier transform of this? What is the Fourier transform? I told you that this is a standard function and you should know the Fourier transform of it, right? E power minus 4t ut, what is the Fourier transform of this? 1 by 4 plus j omega, isn't it? 1 by 4 plus j omega. Now, whenever you are having something like this, if you are multiplying with cos, then what will happen? If this is f of omega, now if you are multiplying with cos omega naught t, so whenever any f of t is multiplied by cos, there will be a frequency shift, isn't it? There will be a frequency shift. This is what we call as a, this is famously called as a modulation property of Fourier transform. This is famously called as a modulation property of Fourier transform, modulation property of Fourier transform, which will be given by 1 by 2 f of omega minus omega naught plus f of omega plus omega naught divided by, already we have written divided by 2 here. So what is omega naught in this case? What is omega naught in this case, my dear students? Omega naught is nothing but 2, isn't it? Omega naught is nothing but 2. We already know f of t, f of omega. Now in the place of f of omega, we have to write f of omega minus 2. F of omega minus 2, it's going to become 4 plus j omega minus 2 plus 1 by 4 plus j omega plus 2. Okay, so 1 by 2, 1 by 4 plus j omega minus 2 plus 1 by 4 plus j omega plus 2. So what I can do now? What I can do now? Let us keep it as it is. Let us keep it as it is. Now we have to find the area of this, right? What we have to do now? We have to find the area of this. Integral minus infinity to infinity. Let me call this function as g of t. And this is g of omega. Can you please tell me how to find the area of this? Integral minus infinity to infinity g of t dt. This will be equal to g of 0. This will be equal to what? G of 0. This is what we call as area property, isn't it? This is the area property of the Fourier transform. The area of any time domain function is given by the frequency domain, put omega equal to 0. The Fourier transform, put omega equal to 0. So g of 0. So if you put omega equal to 0 here, if you put omega equal to 0 here, so it's 1 by 2, 4 minus 2j plus 1 by 4 plus 2j. Okay, so 1 by 2, 1 by 4 minus 2j plus 1 by 4 plus 2j. This is equal to what? 1 by 2. This is 20. And what you will have in the numerator? What do we have in the numerator? It is 8. So this is going to be 4 times and this is going to be 5 times. This is 0.2. So the second part is absolutely correct. The second part is absolutely correct. What about the third one? What about the third one? Hi Aditya. What about the third one? Third one. Rect of t by 2 minus 1. So first of all, let us understand what is rect of t. Whenever you are having something like rect of t by t, rect of t by t, this is nothing but minus t by 2 to t by 2. Minus t by 2 to t by 2, it is 1. Okay. Rect of t by t is going to be minus t by 2 to t by 2, it is 1. Now, if you put t is equal to 1, if you put this capital T is equal to 1, it means that this will be from minus 1 by 2 to 1 by 2. Yes or no? If I put capital T is equal to 1, now t becomes 1, so it's minus 1 by 2 to 1 by 2. Now, I'm sorry, this is not, this is equal to, right? This is equal to. Now, what is its Fourier transform, my dear students? What is the Fourier transform here? The Fourier transform is going to be given by SA function, SA of omega, having a coefficient here, having a coefficient here. What is this coefficient? What is this coefficient? What is this coefficient? This is going to be the area of this rectangle. It is the area of this rectangle. What is the area of this rectangle? Base into height. Base into height, which is 1 unit. Base into height, which is 1 unit. SA of omega, half duration. This coefficient is going to be half duration. This is going to be the half duration. Okay. So it is going to be given by SA of omega by 2. SA of omega by 2. So whenever you are having a rectangular pulse, or what we can call it as a gate function, its Fourier transform is going to be SA function having the coefficient as what? Area. The coefficient is nothing but the area of the rectangle, and the coefficient of omega is the half duration. The coefficient of omega is the half duration. So it's going to be what? SA of omega by 2. This is going to be SA of omega by 2. See, what is SA of omega? SA of omega is nothing but sine omega by omega. Okay, SA of omega is nothing but sine omega by omega. SA of omega is nothing but sine omega by omega. So you are having, so this needs to be known by the student, because students have a confusion between this function and the sinc function. So sinc function is going to be something like this. Sinc of omega is going to be sine pi omega divided by pi omega. Okay, these two are slightly different functions. So coming back, so if you are having rect of t, now it is going to have the Fourier transform as SA of omega by 2, isn't it? It's going to have a Fourier transform as SA of omega by 2. Now rect of t by 2. Before that, let us do the shifting. So if I do shifting, the time shifting property says that you have to have e power minus j omega t naught. T naught is going to be equal to 1. So we have applied the time shifting property of Fourier transform. F of t gives f of omega. F of t minus t naught is going to give you f of omega multiplied by e power minus j omega t naught. Now let us do the scaling. Okay, so this is something like f of t. Now what I want f of t by 2. Now if this is f of omega, can you please tell me what will f of t by 2 going to be? If this is f of t, this is f of omega, then what is f of t by 2 going to be? F of t by 2 is going to be 2 f of 2 omega. Why, sir? Because there is a property which says if f of t gives f of omega by applying the Fourier transform, then f of at is going to give you 1 by mod a f of omega by a. 1 by mod a f of omega by a. So if you put 1 by 2 here, it's 1 by 1 by 2, which is 2 f of 2 omega. Okay, so this is nothing but you're just scaling the time here, t by 2. So in the place of t, you're putting t by 2. So t by 2 minus 1. So rect of t by 2 minus 1 is going to have the Fourier transform as 2 times that of f of 2 omega. 2 times that of f of 2 omega. We already know what is f of omega. SA of, so here f of omega, in the place of omega you're putting 2 omega. In the place of omega you're putting 2 omega. So 2 omega by 2 into e power minus j. In the place of omega you're putting 2 omega. So you're going to have a 2 omega here, right? So this is 2 times that of SA of omega e power minus j 2 omega. 2 times that of SA of omega multiplied by e power minus j to omega. Let us see what is the option saying here. What does the option say? There is no 2 which is present here. The 2 is missing, right? So option C is not correct. Everyone got the same one? Everyone got the 2 here? Everyone got 2 here? Priya says yes, the scaling parameter 2 is missing. Yes, that's correct. Now let us go for option D. What is option D here? 1 by 4 square plus t square. 1 by 4 square plus t square is going to have the Fourier transform as pi by 2 e power minus 2 mod omega. So here again you should know the standard function e power minus a mod of t, right? The standard function e power minus a mod of t should be known. What is the Fourier transform of e power minus a mod of t? The Fourier transform of e power minus a mod of t is 2a by a square plus omega square. if this is f of t, this is f of omega, now we apply the concept of duality. So what does duality say? If f of t gives you the Fourier transform as f of omega, then capital F of t, what is capital F of t? Capital F of omega with omega replaced by t. Capital F of omega with omega replaced by t. So capital F of t is going to have the Fourier transform as, capital F of t is going to have the Fourier transform as 2 pi multiplied by f of minus omega. 2 pi multiplied by f of minus omega. 2 pi multiplied by f of minus omega. So this is 2 times that of, okay, so it is 2 pi times that of, okay. So let us write this, so here, where is the question? Let us go to the question. So you are having 1 by 4 square plus t square. You are having 1 by 4 square plus t square. So 4 square means that the value of a is equal to 4, isn't it? The value of a is equal to 4. If that is the case, e power minus 4t, 4 mod t, will have the Fourier transform as 8 divided by 4 square plus omega square. Okay. Now this is f of t and this is f of omega, right? Now capital F of omega with omega replaced by t. Capital F of omega with omega replaced by t. So 8 by 4 square plus, in the place of omega you are writing t square, will be giving you the Fourier transform as 2 pi times the of f of minus omega, which is 2 pi times the of f of, in the place of t you are going to put minus omega. In the place of t you are going to put minus omega, so it is e power minus 4 mod of minus omega. So it is 2 pi e power minus 4 mod omega. Mod of minus omega is nothing but mod omega. Now again go back to the question and see whether there is a 4 here or not. There is no 4 here. It means I just want for 1 by 4 square plus t square. 1 by 4 square plus t square. So what I will do? I will take 8 to the other side. I will take 8 to the other side. So it will be 1 by 4 square plus t square, which gives you the Fourier transform as, so 8 to the denominator, it's going to become 2 pi by 8. It's going to become 2 pi by 8, which is pi by 4, e power minus 4 mod of omega. E power minus 4 mod of omega. Let us again check with what we got. Okay, so here there is a 2 which is wrong. Here there is a 2 which is wrong, because we have 4 square here. Here we have 4 square here. Okay, so option D is also wrong. Option D is also wrong. It means that what is the correct answer? So option A, option B, option C. Option B is correct. Option A is wrong. Option C is wrong. Option D is also wrong. So the correct answer for this question is option B. The correct answer for this question is option B. So please let me know if I'm doing any calculation mistakes that might happen. Okay. Is that clear, all of you? Have you also got the same value? Have you did the same thing using the concept of duality? Have every one of you used the concept of duality, yes or no? Yes, very good. Okay, so duality is also an important concept. So let us quickly see what are the things that we have covered by solving this problem. One, we have covered the energy concept. Two, we have covered that whenever we are having a function like this, then its Fourier transform is going to be a rectangular pulse. Its Fourier transform is a rectangular pulse. We can directly write it. Third, we have covered modulation property of Fourier transform. This is a standard function. We have seen what is the Fourier transform of this standard function. We have covered the area property here. Next, we have covered rectangular pulse. So what is the Fourier transform of a rectangular pulse? and then we used the concept of shifting and scaling. Then we use the concept of shifting and scaling. We have used the concept of duality. By solving one problem, we have covered so many number of properties of the Fourier transform. Okay, I again wanted to remind you a disclaimer that this question is complex just because we have to solve, we have to cover more number of concepts by simply solving one question. Okay, but in the examination, you might be getting only a single component or two components of this question, complete question. Okay, so nothing to worry, nothing to panic. It is only thing is that you see whether you are able to apply the things correctly or not. You see whether you are making any calculation mistakes or not. You see whether you are able to focus on each and every step that you are doing or not. So these things are important, my dear students. Okay, so with this, we are now going to move on to the next chapter, that is Laplace transform and Z transform. We are moving on to the next chapter, the Laplace transform and the Z transform. Now, again, we are starting with the quiz questions. Okay, so when we talk about the concept of Laplace and Z, there is something called as ROC, which becomes important. And again, you have the properties. That's it. Nothing else is there in the Laplace transform and Z transform concept. We have just know the concept of ROC, and you should know the properties of both Laplace and Z transform. See, Laplace and Z transform both are very much similar transforms, right? One is used for continuous time and the other is used for discrete time. Please answer this question, my dear students. If all the poles are in the left side of j omega axis, the system is causal and stable. Is this correct? If all the poles are present in the left half of the j omega axis, if all the poles are present in the left half of the j omega axis, if all the poles are present in the left side of the j omega axis, let us say that we are having two poles which are present in the left side of the j omega axis, this system is causal and stable. Is this correct? Please try to answer this question. It's a very conceptual question. It's a very basic question, whether this is correct or not. The answer is no. The answer is no. This is the point I'm trying to make you understand or make you realize where we generally do a mistake. We think that if all the poles are present in the left half, the system is directly causal and stable. But what we have to know, what we have to understand is that whenever you are having two poles in the left half, there are three chances of ROC. There are three cases of ROC. The case one is what you are thinking actually. Okay. The case one is you are having a right-sided ROC. Case two, you are having a left-sided ROC. And case three, you are having neither right-sided nor left-sided ROC. Means this area. So you are having region 1, you are having region 2, and you are having region 3. So please understand, my dear students, whenever you are having two poles, here there are three cases of ROCs, R1, R2, and R3. In the first case, where your ROC is right-sided and it is covering j omega axis, ROC is right-sided and it is covering j omega axis, then definitely it is going to be causal and stable. But in this case, it is not covering j omega axis. This is not stable. Here also it is not covering the j omega axis. It is not stable. So what is important here is that in which region we are in, which is not mentioned in the question. Yes or no? In the question, it is not mentioned which region of convergence we are talking about. Because it is not mentioned, then we cannot presume that it is going to be causal and stable. Having said that, the vice versa is correct. The vice versa is correct. If the system is causal and stable, then all the poles are going to be present in the left half. This is correct. But this statement is not correct, that if the poles are present in the left half, we can directly imply that the system is causal and stable. This is wrong, my dear students, because it is only one of the case where this is going to be satisfied. In the remaining two cases, it is not going to get satisfied. So the answer for this question is no. No is the correct answer for this question. Next one, the two-sided Laplace transform of a finite duration signal has no poles. The two-sided Laplace transform of a finite duration signal has no poles. Is this correct? Are you getting benefited by this session? Everyone who is part of the session, are you getting benefited? Are you able to find out your mistakes, what you are doing as a mistakes? It might be silly mistakes, it can be calculation mistakes, it can be conceptual mistakes. I hope you are getting benefited by this session. Okay. So now coming back, the two-sided Laplace transform of finite duration signal has no poles. It does not have any poles, whether this statement is correct or not. Whether this statement is correct or not. Whether it is correct or not. The answer is yes. And this is also been asked in GATE 2020. This is also been asked in GATE 2020. Okay, let us take an example. Let us take an example. Let us have a signal like this. Minus 2 to 2. This signal is f of t. I'll just give an example and then I'll tell you the general way of doing it. Okay, so f of t, let me take the value of amplitude as 1. F of t is going to be equal to, can you please represent it in the form of step? Can you represent this in the form of step? It's going to be given by u of t plus 2, because you are having a step at t is equal to minus 2, isn't it? So we can write u of t plus 2. Here you are having a step at t is equal to 2. So we can write it as u of t minus 2, isn't it? We can write it as u of t minus 2. Now what is the coefficient here, my dear students? What is the coefficient here? What is the coefficient here? The coefficient is nothing but the sudden rise. It is rising from 0 to 1. So final value minus initial value, which is 1 unit. Here it is falling down by 1 unit. So final value minus initial value. So 0 minus 1 minus 1. So that is u of t plus 2 minus u of t minus 2. So what is the Laplace transform of this? What is the Laplace transform of this? U of t, it is 1 by s. U of t, it is 1 by s. U of t plus 2, it is going to be 1 by s multiplied by e power 2s. Minus, again 1 by s e power minus 2s. So what happens here? 1 by s comes as common. You're having e power 2s minus e power minus 2s. Now let us try to expand this e power s. So what is this going to be? 1 plus 2s by 1 factorial, 2s whole square by 2 factorial, plus so on, minus 1 minus 2s by 1 factorial, plus 2s whole square by 2 factorial, so on. Now when you do this, 1 and 1 gets cancelled out. 1 and 1 gets cancelled out. This becomes what? 1 by s. So odd term will be there. This becomes 4s plus 2 times it of 2s cube by 3 factorial plus so on. Something like this will happen. Now you are having s in the denominator, right? So if you bring out s here, so you will have s comes outside, s by s, 4 plus 2. One of the s gets reduced, so 2 cube is still there. This becomes s square by 3 factorial plus so on. So here s and s are getting cancelled out. it means that now this is not having any poles. Now f of s is not having any poles. So you are taking a finite duration signal and checking whether this function is having the poles or not. It is not actually having any poles. Okay, this is one way of doing it. The other way of doing it is the just checking the existence condition of the Laplace transform. Existence condition of the Laplace transform, because after all, the concept of ROC comes from the same. The concept of poles will also come from the same. Okay, so what you can do, the other method one is that you take any finite duration signal and see whether you are having any poles or not. Okay, that is an example based method. Whenever you are not able to understand whatever is given is correct or not, then what you can do is that you can just take an example. You just take an example and see whether it is getting satisfied or not. If it is getting satisfied, then very happy. If it's not getting satisfied, then also very happy. Okay, the other method is that you have to see the absolute integrability of f of t e power minus sigma t. You have to see the absolute integrability of f of t e power minus sigma t. You just change the different values of sigma. You just change the different values of sigma and see whether this is going to be absolutely integrable or not. You see whether by changing the different values of sigma, whether this is going to be absolutely integrable or not. You will find out that this is going to be absolutely integrable for each and every value of sigma. You will find that it is going to be absolutely integrable for each and every value of sigma, which means that everywhere it is going to be defined, there is no point of being undefined. There is no point of being undefined. So the statement is correct. Whenever you are having any finite duration signal, then you are not going to have any poles. Next one. The Laplace transform exists for every signal which may or may not have Fourier transform. The Laplace transform exists for each and every signal which may or may not have Fourier transform. Is this statement correct? Is this statement correct that the Laplace transform exists for each and every signal which may or may not have Fourier transform? The answer is no. The answer is no. See what this statement says. Doesn't matter whether you are having Fourier transform or not. Doesn't matter whether you are having Fourier transform or not. The Laplace transform exists for each and every signal. Remember, for Laplace transform to exist, it has to satisfy the existence condition. It has to satisfy the existence condition. If this condition is not satisfied, then you cannot have Laplace transform. So telling this is wrong, that Laplace transform exists for each and every signal. You consider a signal f of t is equal to 1. And you are talking about the two-sided Laplace transform. Okay, this signal 1 is not going to have any Laplace transform. Whereas 1 does have the Fourier transform. 1 does have the Fourier transform, but 1 does not have the Laplace transform. So it means that the Laplace transform does not exist for each and every signal. But yes, for quite a few signals where you do not have Fourier transform, you have Laplace transform. This statement is correct that there are a lot of signals, lot of useful signals for which we did not have the Fourier transform, but we had Laplace transform. This is correct. But generalizing this for each and every signal is wrong. Generalizing this for each and every signal is wrong because there are signals just like here, f of t is equal to 1, which has a Fourier transform, but it does not have the Laplace transform. Okay, so you should be a little careful while answering the questions. Okay, next question. If the signal is non-causal, the ROC is right-sided, neither right-sided nor left-sided. If the signal is non-causal, then the ROC is neither right-sided nor left-sided. Is this correct? This seems to be correct. This seems to be correct, isn't it? If the signal is non-causal, then the ROC is neither right-sided nor left-sided. Okay, please answer me the question. What is U of t's Laplace transform and ROC? What is U of t's Laplace transform and ROC? The Laplace transform of U of t is 1 by s. The Laplace transform of U of t is 1 by s. A Laplace transform of U of t plus 1 is 1 by s into e power s. Correct? But both of them are going to have the same ROC. It means that because the time shifting property will not affect the ROC. The time shifting property will not affect the ROC. So U of t is having 1 by s. U of t plus 1 is 1 by s e power s, having sigma greater than 0. Now, U of t is a causal signal. U of t plus 1 is a non-causal signal. U of t is a causal signal. U of t plus 1 is a non-causal signal. Yes or no? But both these signals are right-sided signals. Both these signals are right-sided signals. Okay. So here the ROC is right-sided. So what we have to understand is that if the signal is tending towards right side, the ROC will be right-sided. Here, even though the signal is non-causal, still you are having the ROC which is right-sided. So this is very important here, my dear students. It doesn't matter whether it is causal or non-causal, but what is more important is that whether the signal is right-sided or not right-sided. Right-sided signal will have the ROC which is also right-sided. The right-sided signal will also have the ROC which is right-sided. Left-sided signal, what is a left-sided signal? If you take a signal which is opposite to this, if you take any signal which is opposite to this is a left-sided signal. So here the ROC is going to be left-sided. If you are having a combination of a signal which is something like this, let us say, it's just an example. Now this is a signal which is neither right-sided nor left-sided, which is both-sided. Now this is a signal which is going to have a both-sided ROC, or a neither right-sided nor left-sided ROC. Neither right-sided nor left-sided ROC. Hi Nimish. Neither right-sided nor left-sided ROC. Okay. So there is no denial of the fact that if you are having a causal signal, the ROC will be right-sided. No doubt about it, because causal signals are actually right-sided. If you are having anti-causal signal, the ROC is left-sided. There is no doubt about this. This is correct. But we cannot say that a non-causal signal will always have neither right-sided nor left-sided ROC. This is wrong, because a right-sided signal, which as an example is a causal signal, is going to have a right-sided ROC. A left-sided signal, one of the specific example is an anti-causal signal, is going to have the left-sided ROC. So anti-causal signal is just an example of a left-sided signal. Causal signal is just an example of a right-sided signal. Okay, so telling that if you're having a non-causal signal, the ROC is going to be neither right-sided nor left-sided is wrong. Okay, so if you're having a signal which is both-sided, which is something like this, then you can have the ROC which might be neither right-sided nor left-sided. Okay, now the next question, everyone. The Fourier transform can be obtained from Laplace transform of any signal by substituting s is equal to j omega. By substituting s is equal to j omega, you can get Fourier transform from Laplace transform. Is this correct? Is this correct to say that you can just directly get the Fourier transform from Laplace transform by just substituting the s is equal to j omega? The answer is no. The answer is no. Let us take an example. You are having e power 2t u of t, e power 2t u of t, which has the Laplace transform as 1 by s minus 2. But this signal does not have Fourier transform. Does not have Fourier transform. Now you cannot say that, sir, I will substitute s is equal to j omega. Now I will get the Fourier transform. This is wrong. This is wrong, my dear students. You can put s is equal to j omega only when this signal is going to be satisfying absolute integrability. Only when the signal satisfies the absolute absolute integrability, then only we can substitute s is equal to j omega. Otherwise, we cannot substitute s is equal to j omega. Yes or no? Otherwise, we cannot substitute s is equal to j omega. So the answer for this question is no. The answer for this question is no. That for any signal which is having a Laplace transform, you cannot find out the Fourier transform. If you want the Fourier transform, first you have to check the existence condition, and then only if this condition is satisfied, then you can put this. I'm sorry. Is that clear, all of you? Is that clear? Yes. Can we apply Fourier transform for unstable system? Can we apply Fourier transform for unstable system? Fourier transform cannot be applied for unstable system. Fourier transform cannot be applied for unstable system. Why? For a stable system, what is the condition again? The condition remains the same. The impulse response has to satisfy absolute integrability, right? The impulse response has to satisfy absolute integrability. Now, if you see, the condition for the Fourier transform and the condition for stability both are same. The condition for Fourier transform and condition for stability both are same. Yes or no? So, if the system is stable, then only you can find out Fourier transform. If the system is not stable, then you cannot find out the Fourier transform. This is also important. So what are the limitations of Fourier transform? These are the two limitations. Fourier transform cannot be applied for unstable system. Fourier transform cannot be applied majorly for unbounded signals. Majorly for unbounded signals. These are the two points that we have to keep in our mind when we are talking about the Fourier transform. Okay, so these are the limitations. That is the reason why, just to overcome these limitations, we go for Laplace transform. So many students have this assumption that, okay, I will put s is equal to j omega, I will get the answer of Fourier transform, but no. Okay, this is not correct, right? So I think we can stop here. We will have one more session, part 3, where we will cover the remaining part, that is the Z transform and the discrete time Fourier analysis. So that will be a short video. It will be maximum 1 hour video. So in which we will cover the remaining part. Okay. So before ending the session, you can take this problem. We can discuss this in the next session. So when we come for our next session, then we will be discussing this problem. Okay. So meanwhile, you can also try from your side. So what are the things that we have learned in today's session? If you're having any doubts, you can ask. The things that we have learned in today's session are, we have majorly focused upon the concept of Fourier series and Fourier transform. We have majorly focused on the concept of Fourier series and Fourier transform. Yes, at the start, we have solved a problem from LTI systems and we are moving towards the Laplace transform. But majorly, if you ask me what is the important thing that we have discussed, that is the Fourier series and Fourier transform. Fourier series and Fourier transform, It is actually not difficult. It just requires more practice from your side. Okay, if you are struggling with your third chapter, which is Fourier analysis, then it is high time that you have to solve the problems from this chapter. Solve the problems and then take the test series. That will be quite beneficial for you. Okay, so the students who have missed the last session, so in which we have discussed about the chapter 1 and chapter 2, please do attend the session. If you are liking our sessions, please like and share this video with your friends, and also subscribe to this channel. Okay, please subscribe to the channel. Right, so if you're having any doubts, you can please ask. If you're having any doubts, you can please ask. If you're not having any doubts, then you can leave the session. Wish you all the very best. Let's meet in the next session, that is part 3. Okay, and keep your preparation with full energy, full josh. Okay, don't waste your valuable time. We are just into last 50 days. The GATE exams, schedule is also announced, right? So we have to be more focused. Never lose the confidence till the end. Okay, if you are doing mistakes, try to avoid the mistakes. Keep the learnings with you, but don't get disappointed. Don't ever entertain the thought of quitting here. Whatever you have studied till now will go waste if you quit here. Okay, so please don't think anything like that. Please try your best effort, because it is not only about GATE examination. There are so many other competitive examinations which are revolving around the concept of the GATE syllabus. Okay, so it's very important that you have to do your best. Okay, every test series is important. Don't take test series lightly. Okay, so you have to take test series very, very importantly, and take as many test series as possible. More importantly, you have to analyze every test series. Whatever test series you are doing, after completing the test, you have to analyze where you are making silly mistakes, what are the areas of improvement. All these things you have to note it down. Hi Nivedita. So if you're having any queries, please ask, my dear students. So any other challenges you're facing as part of your preparation? Ranjita, if you're a the GATE Academy student, then you have a doubt solving portal. Okay, so in the doubt solving portal, you can post your queries. We don't have any official TGA WhatsApp group. It becomes very difficult to manage a WhatsApp group. Okay, but if you're having any queries regarding this session, then you can post. You can either ask me now, or you can post in the the comment box. Okay, so I think we can stop the session here. Okay, can we stop? Anything else to discuss? Can we say tata bye bye? Okay, so let us stop the session here. Thank you all of you, and let's meet in the next session.